Welcome back to part 2 of 4.7. So find each of the following limits. The limit as x approaches 0 of the cosine of x minus 1 over x squared minus x. So this was the one of the graph we were looking at. So pretty much, again, make sure you guys are establishing that the limit as x approaches 0 of cosine of x minus 1 equals 0, right? And then separately, again, the limit as x approaches 0 of x squared minus x. Again, it's just 0 minus 0, so that's going to give us another 0. So therefore, we can apply, again, L'Hopital's rule, right? Apply L'Hopital. All right, so that means we're going to take the derivative on top. So we're going to have the limits as x approaches 0 of the derivative of cosine of x would be negative sine of x. Derivative of negative 1 is just 0 over derivative at the bottom. We're going to have 2x minus 1. We plug in 0 here, we're going to end up with negative sine of 0, which is 0. And then 2 times 0 is 0 minus 1. We get 0 over negative 1, which is just 0. So that is a value, right? So you can say that the limit of the cosine of x minus 1 over x squared minus x is equal to 0. All right, moving on to part B. So we have the limit as x approaches 1 of the natural log of x minus x plus 1 over e to the x minus e times x. So here e is just a constant, right? And then from there, what we want to do is pretty much just set it up so we know what we're doing again, right? Separately first. So we're going to say that the limit as x approaches 1 of the natural log of x minus x plus 1 is equal to 0, right? The natural log of 1 is 0. 1 negative 1 plus 1 gives me 0. And then the limits as x approaches 1 of e to the x minus e times x, that's going to be just e minus e, which is again 0. So therefore, again, right, therefore you're going to apply L'Hopital's rule. All right, and then from there, the derivative on top, we're going to say that the derivative of, so first, we're going to say the limits as x approaches 1, derivative of the natural log of x is 1 over x minus 1, right? Derivative of x is just negative 1 in this case. Derivative at the bottom, we're going to have e to the x minus e. That's it. All right, so here again, if you do plug in 1, you end up with 1 minus 1, right? So you end up with 0 over 0. Again, see, I'm using an arrow, not an equal sign for that. Same thing at the bottom. So we're going to apply L'Hopital's rule one more time. So we're going to say that the limit as x approaches 1. And in this case, we're looking at 1 negative, right? Derivative of 1 over x is going to be 1 over x squared, negative 1 over x squared. Derivative at the bottom is just going to be e to the x. This is a constant, so it goes away. Plug in 1, you're going to end up with negative 1 over 1 squared, or just negative 1 over e. And that's going to be our limits. And then part C, the limit as x approaches infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4. So again, this is one of the problems that you guys were looking at initially. So we're going to say that the limit as x approaches positive infinity of 1 minus 4x minus 5x squared. It's pretty much an unbounded parabola which points down, and that goes towards negative infinity. Right? So in this case, the next one, the limit as x approaches positive infinity of 3x squared minus x minus 4 also approaches, in this case, would be positive infinity because our parabola here in this case opens up. So now we can say that we can apply, right? So therefore, we can apply L'Hopital's rule, right? So, okay. So here we're going to take the derivative on top. We end up with the limits as x approaches infinity. Let me do a different color. Here is going to be negative 4 minus 10x. And then derivative at the bottom, we end up with 6x minus 1. And then here, again, we end up with the top is a line that points down. So it goes towards negative infinity. And the bottom is a line that points up. So it's going to be going towards positive infinity. So again, make sure you guys are using an arrow because this is not a numerical value. So we can apply L'Hopital's rule one more time. And here we're going to say that the limits as x approaches positive infinity, derivative on top is just going to be negative 10. Derivative at the bottom is going to be positive 6. So therefore, we're going to say this goes towards negative 4/3. So the derivative, right? The derivatives of 1 minus 4x minus 5x squared over 3x squared minus x minus 4 equals negative 4/3. So here you use equals because it is a numerical value. And then looking at, uh, pretty much looking at part uh, D, right? I do want to note that if you guys look at here, we didn't have to apply L'Hopital's rule one more time because we could also just look at the leading coefficients because they do have the same value, right? And we would end up with negative 4/3 once we simplify that. But now move on to part D. So here we're going to say that if we do apply the limits, this would be a parabola that opens up. So the limit as x approaches positive infinity of 4x squared minus 5x plus 2 equals positive infinity, right? Or not equal, sorry, goes towards positive infinity. And the bottom, the limit as x approaches positive infinity of e raised to the 5x plus the natural log of x also goes towards positive infinity. And then from here again, we want to apply L'Hopital's rule. So we're looking at, right? So therefore, L'Hopital applies, right? So apply L'Hopital's rule. Okay. So from there, we're going to say the limit as x approaches positive infinity. The derivative on top, we're going to have 8x minus 5. And at the bottom, we're going to have 5 times e to the 5x plus 1 over x, right? The derivative of the natural log of x is 1 over x. And then from there, again, we plug in infinity, and we end up with pretty much, again, the same thing, right? So we're going to end up plugging in L'Hopital. So this goes towards positive infinity over positive infinity. Apply L'Hopital rule one more time. So here the limit as x approaches positive infinity. We end up with 8 on top. At the bottom, we're going to have 25 e to the 5x minus 1 over x squared. All right. And then if you plug in infinity here, this goes towards 0. So you're going to end up with 8. And then here you get infinity. So in this case, this is going towards 0. So we're going to say that the limit for this is equal to just 0. And then now looking at example 3. So find each of the following limits. The graph of f of x is shown below. Right. So it says find the limit as x approaches 3 of f of x over x squared minus 9. So here, if I do approach 3 from both the left and the right side, you notice we are going towards 0. So this is going towards 0. And then this is x squared minus 9. So that's going to be 3 squared is 9 minus 9. It's also 0. So again, make sure you guys are using the arrows. They won't take away points if you use the arrows because you're just indicating that, right? So we do want to make sure that we say that the limit as x approaches 3 of f of x equals 0, and the limit as x approaches 3 of x squared minus 9 equals 0. So from there, we're going to end up with applying L'Hopital's rule. So we're going to say that the limit as x approaches 3 of f prime of x over 2x. Now, to figure out the derivative, we just have to figure out the slope between these 2 points right here. And in this case, it's just negative 2 over 1. So that's going to be, at 3 is going to be negative 2. And then 2 times 3 is 6. So that gives us negative 1/3. And that would be our derivative at that value. All right. And then part B here. So we're looking now, in this case, at a table, the functions f of x and g of x are differentiable for all x. So we'll use the following table to find the limits. So now if we do want to figure out the limits as x approaches 2, we're going to have 4. So f of x, 4 minus 4 equals 0. And then that's been established. And then the limit as x approaches 2 of g of x times x squared. In this case, is going to be just 0 times 2 squared, which is still 0. So again, it's been established. So we're going to say, therefore, we can apply L'Hopital's rule, right? Just make sure you guys write it out. I've just been doing it like that to save some time. And then from there, we're going to take the derivative. So here, change color a little bit. So we're going to say that the limits as x approaches 2 of f prime of x divided by In this case, at the bottom, we do have to use the product rule. So be careful because there is a product right there, right? So we have g of x and then x squared. So it's going to be g prime of x, 2x, right? And then draw your fish. So you end up with g of x times 2x plus x squared times g prime of x. Oops. And then we plug in 2. So now we're looking at f prime of 2, which would be negative 2 over g of 2, which is 0 times 2 times 2, plus 2 squared. G prime at 2 is positive 3. So nice. This goes away. We end up with negative 2 over 4 times 3, which is positive 12, or negative 1 over 6. So we're going to say that this is equal to negative 1 over positive 6. And then lastly, we're going to look at example 4. So from the 2018 AP Calculus exam AB, question 5, let f of f be a function defined by f of x equals e to the x times cosine of x. Let g be a differentiable function such that g of pi over 2 is equal to 0. The graph of g prime, the derivative of g, is shown below. Find the value as the limit as x approaches pi over 2 of f of x over g of x, or state that it doesn't exist, and make sure you justify your answer. So what we want to do here is, again, they're telling us f of x. I'm going to rewrite it over here. F of x equals e to the x times cosine of x, right? If I do plug in pi over 2 here, we're going to end up with, so f of pi over 2, right? So, well, I'll plug into the limit, not into the function itself, right? Sorry about that. So here, let's do that. So we're going to say the limits as x approaches pi over 2 of e to the x times cosine of x. So this is equal to 0 because we have e to the pi over 2. Cosine of pi over 2 is 0, so that's just 0. And then we have our function g of x. G of x, they're stating exclusively the g of x. Since it is a differentiable function, that means it has to be continuous. So we know that the limit as x approaches pi over 2 of g of x also is equal to 0, right? Because again, g of x is continuous. And remember, differentiability does state continuity, but not the other way around, right? So here, once we state that, so we can say again, therefore we can apply L'Hopital's rule. And then we're going to do the limits as x approaches pi over 2. The derivative on top, we're going to have e to the x and then cosine of x. Again, make sure you guys are drawing your fish, right? Product rule, sorry. So this is going to be e to the x, and this is going to be negative sine of x. So here we're going to have negative e to the x sine of x plus e to the x cosine of x over g prime of x. All right, we know that at pi over 2, we're going towards positive 2. So it makes a nice number. So here we start plugging things in. So we're going to have the limits as x approaches, well, not anymore, actually, we plug it in. We'll have to state it again. So here we're going to say that negative e to the pi over 2 times sine of pi over 2 plus e to the pi over 2 times cosine of pi over 2 all over g prime at pi over 2. So this is going to be equal to, this is just negative e to the pi over 2, and then times sine of pi over 2 is just positive 1, and then e to the pi over 2 times 0 gives us 0. So we just left with negative e to the pi over 2 divided by g prime at pi over 2, which happens to be positive 2 right there, and that's pretty much our answer. And that's it. So again, just make sure that, since you have to remember here, the key is that we can say that g of x is differentiable. Therefore, it is continuous, right? So that is one of the key things that you guys have to think about here, right? If it's differentiable, it's continuous, but if it's continuous, it's not necessarily differentiable.